We mentioned COD when we were talking about normalization, the key, the whole key, and nothing but the key, so help me COD. Who is this character, COD? Well, there he is. He has passed away in 2003, but he is basically the guy behind relational databases. And we want to take a look at some of the guidelines that he has established to kind of determine whether or not we're using a relational database sort of as intended, or if a relational database that claims to conform to sort of the expectations that he had around relational databases actually meets those expectations. These remarks of his, or these ideas of his, were published originally in a couple of articles in the trade magazine Computer World, which is kind of a big magazine that's read by, chief information officers and database administrators and those types of folks. And there were two articles in 1985 called "Is Your DBMS Really Relational?" and "Does Your DBMS Run by These Rules?" Now, the original intent of this was to kind of address the marketing hype of all of the various database manufacturers that were coming out and saying, hey, our database is relational. Because at this point, relational databases were relatively new, and they were seen as kind of the next coolest thing, and everybody wanted to jump on that bandwagon. And what COD was trying to do was basically say, hey, this is what relational databases really are, and as you're thinking about adopting one of these vendors' products, you might want to take a little step back and ask very clearly whether or not the product that you're looking at actually conforms to these expectations. The articles are still quite relevant and are often cited, and I'm kind of coming at this from the perspective of us sort of understanding what's gone into relational databases as opposed to being a tool that you would use maybe to evaluate a relational database going forward. Because at this point, some 30 years on, 40 years on almost, we're pretty well conforming to these kinds of expectations. But I just want to, again, use this as sort of a historical framework to give you a picture for what these databases do and to give you some idea about where some of these capabilities maybe came from back in the Stone Age of databases. So here's rule 0. For any system that is advertised as or claimed to be a relational database management system, that system must be able to manage databases entirely through its relational capabilities. Let's unpack that a little bit. The idea here is basically to kind of exclude products that were not relational. There were a lot of other models for databases that were being bandied about at the time, network models and hierarchical models and other sorts of things, that because relational databases were sort of becoming all the rage, we're trying to recast themselves as being really relational, right? And so this rule is basically a way to kind of say, hey, that's really not a relational database, principally because it doesn't let you manage the database through its relational capabilities. You have to kind of work around the database itself in a different way than what it purports to provide as relational abilities in order to be able to add new data, to modify existing data, to administer the database itself. And that therefore excludes those kinds of databases that were not truly relational. Now, we're kind of seeing the pendulum swing again in the last few years. We've seen the emergence of other types of databases that we're going to talk about in this class. The document databases like MongoDB, key value databases like Redis. And I don't view those as databases that are kind of abandoning hope and going back to old school models that aren't relevant anymore. I sort of see those as complementary technologies that we can use in addition to a relational database. And again, right back to the very first day of this course, I want you to be able to understand these different models for data persistence in order to be able to choose the right database for the job. And in a very large number of cases in practice still today, relational databases are going to be the bread and butter of a lot of your data persistence, unless there's specific reasons to go elsewhere, like to document or key value databases. So although in the early going, this rule 0 was really there to try to differentiate non-relational databases that were trying to masquerade as relational, now today, I think it's just sort of an admission that, hey, relational isn't the only game in town, and that's okay. Okay, rule number 1, information. All information in a relational database is represented explicitly at the logical level in exactly one way, values in tables. So this is the whole issue of it's tables all the way down. Everything in the relational model is a table. Even a single cell, or what looks like a scalar value that you get back from a relational database query, if you're only getting back a single column with of a single row, that's still a tiny, tiny table, right? It's a table with one row and one column and one value in it, but it's still a table. And that's going to be the case throughout the relational database. Note that it's saying here at the logical level. Now, this doesn't say anything at all about what's the most efficient way to store these data on disk or to use the network efficiently or anything like that. As long as, from a logical point of view, anybody who's using the database and not an implementer of the database itself interacts with it just by merit of using tables. So one of the things that was happening at this time when we wanted to create relationships between items stored in other types of databases, say a network database, we'd have to create what were referred to as hard-coded links, right? You're going to say, in order to capture a relationship between datum A and datum B in another style of database management system, you'd have to go in there manually in your code and create some kind of a link between those two data. So it's completely up to a programmer to make changes to that. You can't access it using a query language, right? There's just a whole lot of restrictions associated with that. And what COD is saying is, hey, it's tables all the way down. And it's even tables in the sense of how do we maintain relationships from one table to another or from one relation to another. And we know, of course, now that we use the primary key, foreign key relationship in various combinations to do that, but it's still values that are being stored in tables that carry all the information in the relational model. Rule 2, each and every datum, so by datum we mean sort of atomic value, right, the individual values that are stored in a cell of a table, in a relational database is guaranteed to be logically accessible by resorting to a combination of table name, primary key, and column name. And this doesn't seem particularly earth-shattering to us today, right? Because that's what we're used to doing when we're dealing with a relational database. But coming down and saying, hey, this is the one and only way you're going to use to access any of the data in your entire data persistence mechanism was pretty revolutionary at the time. So we can get to every datum by looking at that table key column triplet. We don't have to have any kind of goofy workaround to get to that, right? We don't have to resort to special purpose code or other kinds of libraries or anything like that. Everything in the system is accessible using that exact same model. One of the things also that this implies is that we have a unique primary key, right? Because if we're going to go to specific individual accessible, addressable values in our data store, we've got to be able to find it uniquely. That's guaranteed access. Rule number 3, null values. Null values, distinct from the empty character string or string of blank characters and distinct from 0 or any other number, are supported in fully relational DBMSs for representing missing information and inapplicable information in a systematic way independent of data type. Again, this seems like kind of just bread and butter database stuff, but this was a big deal at the time, and you can see from this kind of parenthetical expression here that COD is explicitly rejecting the use of other tricks that have been employed over the years to indicate we just don't know the value. So empty character string, blanks characters, 0, or any other number, none of those are valid to indicate what COD conceives of as the null value. So the null value is actually a separate thing, right? It's not equal to any number. It's not equal to any string. It's not even equal to itself. It's just a unique thing that is used to indicate I don't know, or the information is missing, or similar kinds of semantics that are attached to the null values. But the key idea here is that it's distinct from everything else. So null usually just means unknown, and it differs from every other value. And importantly, null is always the same null. So if you see null any place in a database or in a query, there's only one null, which is a great example of the 0-1 infinity principle, right? There's only one way to represent the I don't know value, and that's with null. There aren't more than that, and there is only this special the special value. As an aside, the result of having a null value in the language of the database and in the way that it stores information means that we actually are extending our logic that we use when we're doing comparisons in the database to, instead of being a 2-valued logic of true and false, it's actually a 3-valued logic of true, false, and null. And you can see that the presence of the null value has some interesting implications. So this truth table, right, it just shows two values, P and Q, and then P or Q, P and Q, P is equal to Q, and not P. These have the values that you'd expect them to have for the ordinary Booleans, right? True, 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 false, false, true, and false, false. We're used to those, but as soon as we introduce a null value, then suddenly we've got a little bit different semantics. So if we take P equal to true and Q equal to null, we see that, well, P or Q is still true, but P and Q, or P is equal to Q, an equality comparison, both give the value null. Similarly, for false and null, we get actually nulls except for the and case, which we know to be false, because as long as we have one false conjunct in this conjunction, the result is going to be false. And then there's the other combinations that are listed here. I'm not going to belabor this table, but I think it's important, first of all, to keep in mind that null is going to be evaluated differently in a Boolean context, which we see a lot, right? In where clauses, in having clauses, and so forth. So it's important to be aware that null is treated somewhat differently, and it's probably worth your time to spend a little bit of time just working through each of these examples to understand how null affects the usual logical operations, because some of it is surprising. So for example, like here, when P is null, not P is also null, right? It just doesn't quite behave the same way as the Boolean values, but it's really important because it finds itself in the database model in a very fundamental sense. Rule number 4, online catalog. The database description is represented at the logical level in the same way as ordinary data, so that authorized users can apply the same relational language to its interrogation as they apply to the regular data. So we're used to thinking about the contents of a database as application data, right? It's information that we want to store for our business or organization or whatever. And we cast that in terms of the tables and the relationships between the tables as connected to the particular application we're dealing with. Now, what this rule is saying is that in addition to treating application data in that fashion, we should also be able to understand the structure of the data itself in the same fashion. So the database description, what's contained in the database? What are the tables that are in this database? What are the rows, what are the columns that are in those tables? All those pieces of information can actually be interrogated using SQL from a relational database. So I can go and ask the database, hey, tell me the list of the tables that you currently store. And I'm going to do that by making a SQL query against a specific system table whose job it is basically to keep track of a representation of all the tables in the database. There's going to be another way I can use SQL to query for all of the columns in a particular table, for example. And I get not only the column name, but the type, the default value, any other constraints that are associated with that. All that information is available to me by doing a query that looks exactly like the queries that I do when I'm trying to access ordinary application data. Now, this is a big change. So analysis here, the metadata, right? The data about the data. What are the names of the tables? What are the columns in this table? What type does each of those columns have? That's data about the database structure, or metadata, is also logically stored as tables. Sometimes this is referred to as the data dictionary, the details of what data are stored in a particular database. Some older sources will refer to that as the catalog. So it's kind of like a catalog, right? You can look it up and see what you can purchase from a company. This is a way to let you look up and see what information is available in the database. Another type of metadata that's accessible in this similar way is configuration parameters. So there's, in any database except maybe something small like SQLite, there's a boatload of ways that you can kind of tweak and tune the database to behave different ways. The sizes of tables, the amount of disk space they can take up. There's just tons of little knobs and dials that you can twist. And what COD is saying here is that all of those things, whether it's data about the data or if it's configuration parameters, we want to be able to access that in exactly the same way that we access our normal application data. Now, of course, in practice, the ability to access that metadata or those configuration parameters is going to be pretty tightly controlled, because you don't want any mere mortal user getting in there and monkeying with the fundamental structure of the database by accessing this metadata. So it's usually restricted to an account that owns the database or something like that. But once you have the permissions, the means by which you access that information is exactly the same as the means by which you access your ordinary data. And this was in rather dramatic contradistinction to the way that you did this for other kinds of data management systems at the time. You'd have a special interface, you'd have a special API, you'd have a special application that you'd have to go through and learn and train people on and whatnot to be able to do database administration. And what COD is saying is, hey, that's stupid. Let's just use this awesome data access mechanism we already have in the form of SQL, and using the tabular abstraction with tables and rows and columns in order to do that job for us. Rule number 5, this one's kind of a mouthful here. Comprehensive data sublanguage. A relational system may support several languages and various modes of terminal use, right? No notion of mice and icons and stuff here at this point. For example, a fill-in-the-blanks mode, where you can just kind of get a form on your screen and sort of tab from field to field. However, there must be at least one language whose statements are expressible per some well-defined syntax as character strings, and that is comprehensive in supporting all of the following items, right? So he's saying we got to have one special language that can do a whole bunch of stuff that we want to be able to have access to in a relational database. So it should do all of the following things: allow you to define data, like construct the shape of a table, allow you to define the way that you can do viewing of the data. We'll talk about views later on. Manipulate the data, change it, do the CRUD operations basically, right? Create, read, update, delete. Allow you to express integrity constraints, things like primary keys are unique and foreign keys refer to existing rows in another table that have a specific primary key. That allow you to define authorization, who's allowed to access the database, and then what are they allowed to do once they get there. And then transaction boundaries, right? Being able to say that I want to have a certain set of operations all succeed or have none of them succeed in case something goes haywire in the process. So we need a language to do this. We call it SQL. Okay, so that's kind of a nice catalog of the kinds of things that SQL can do. It should mention here that I think that people differ on how they say that acronym. Some people say SQL. I tend to say that. Some people pronounce each of the letters. It's kind of, that doesn't really matter which way you do it. Where it gets troublesome is if you're reading it in print, because if you pronounce it in your head SQL, you'll want to have a sentence that says something like an SQL query, whereas if you say SQL, you'll want it to be a SQL query. So in some cases, it begins with a vowel sound, and in some cases, it begins with a consonant. Rule 6, view updating. All views that are theoretically updated are also updatable by the system. Now, this is something that we might not be familiar with, but we are going to spend a couple of days talking about views. So we'll just kind of punt on this rule until we have a better understanding of those. Rule 7, high-level insert, update, and delete. We've kind of been referring more often than not to the ability to retrieve data from the database, and this rule basically says we should be able to do the other operations in the CRUD pattern as well. So the capability of handling a base or derived relation as a single operand applies not only to the retrieval of data, but also to insertion, update, and deletion of data. So this basically says we can do all the CRUD operations. Then that's a super common acronym in database circles, and it basically corresponds to the 4 basic things we can do to data. We can create new data, we can retrieve existing data, we can update existing data, and we can delete existing data. Sometimes the R is referred to as read. I think retrieve is a little bit clearer. So again, not super surprising, but not obvious either at the time that COD was making these rules, that we should be able to not just use this as a query language to extract data, but also use the same mechanism, the same SQL language, right, to update the contents of the database. Rule 8, physical data independence. application programs and terminal activities, right, this is again kind of old school reference to using a terminal, remain logically unimpaired whenever any changes are made in either storage representations or access methods. So, the second part of this statement is really referring to this notion of physical data. How are we storing the information? Where is it stored? What kind of hardware is it stored on? How are we providing access to those data? What he's saying is that those kinds of concerns should not be things that the application developer is aware of, really. The application programs and then these terminal activities like those fill in the form kinds of things, but application programs shouldn't have to care about that stuff. The program should be able to be written in such a way that those physical implementation details should be invisible to the application at a lower level of abstraction. So the user is unaware of the physical details of the storage. Rule 9, logical data independence. Again, this has to do with application programs and terminal activities. They remain logically unimpaired when information-preserving changes of any kind that theoretically permit unimpairment are made to the base tables. What does that mean? Well, in one sense, we're saying here that changing one part of the schema doesn't affect the other parts, right? We should be able to make changes to portions of the structure of the data without having it inadvertently and adversely affect other things. The key phrase here really is information preserving, right? When we make information preserving changes, which means that we're basically not losing any information, we shouldn't really notice that from the point of view of the application program. Of course, there are certain changes that we could make using the standard mechanisms that would not be information preserving. So, for example, deleting a table will probably result in some sort of impairment to the application's logical consistency or ability to fetch the data. But within reason, making other kinds of changes should be logically unconnected to the portions of the system that aren't being modified. Integrity independence, Rule 10. So integrity constraints specific to a particular relational database must be definable in the relational database sublanguage, that's SQL, and storable in the catalog, not in the application programs. Okay? So, for example, some integrity constraints that are specifically in view. Entity integrity, for example, that of a primary key in a table is never allowed to have a null value, right? Because there is only one null value across the entire database, and kind of by definition, that means that we won't be able to uniquely identify more than one row in that table. Or referential integrity, where we have to make sure that we have a primary key in the table that a foreign key refers to, so that we can't have a foreign key that refers to either a non-existent table or a foreign key that refers to a row in a table where that row is not present. So those kinds of integrity constraints need to be able to exist. And importantly, well, there's two other pieces here. Definable in the relational data sublanguage, right? That's SQL. And we'll see that we can define integrity constraints using the SQL data definition statements. And also, they're stored in the catalog, not in the application program. So by saying that, COD is telling us we shouldn't rely on the application program to maintain these constraints on the integrity of the data. Not that we wouldn't be able to do it in our application program, but there's two issues there. One is that, well, we might screw something up in our application, and the other is that we're going to have to maintain those same integrity constraints in any application that's going to access that same database. Better to have the database itself be kind of the final arbiter of whether or not an activity or an action is possible by having the constraints implemented in the database. And in order to make that convenient, that's kind of why we want to be able to define it in terms of the relational data sublanguage or in terms of SQL. One of the concerns that was present here that I didn't mention is that some of these early databases didn't support referential integrity, right? The reason being, it was seen as a potential drain on performance. For example, if you're trying to enter a new row in a table that has a foreign key relationship to a second table, you've got to make sure that the value that goes into that newly inserted row for that particular foreign key actually refers to an existing row in the second table whose primary key matches the foreign key that you're putting in. Now, just because we have to go out to another table, we have to read it in, we have to search for that key, there's quite a lot more going on there than just inserting new data in an existing table. However, if we don't do that check at the time that we insert those new data, we are materially damaging the ability of the database to maintain that integrity. So some database vendor says, well, this isn't really that important and it's going to be too slow. I think, well, certainly by modern standards, that might have been true because the machines were just a whole lot slower at that point. However, I think on balance, it's probably worth it to pay that price, even if you have a slow machine, so that your data doesn't get completely broken. Currently, certainly, the default behavior is going to be to impose these relational and other types of integrity constraints all the time on the tables that we're using in our relational databases. Rule 11, distribution independence. A relational DBMS has distribution independence. Now, what we're saying here is that the database itself could be physically located pretty much anywhere we want it to be located. The difference is that it should still appear as if the data is just stored on a single computer, even if we've split it up onto many other computers. And this is when we, later on in the semester, we're going to start talking about database scalability. And we'll see that one way to scale data, or one way to scale a database is what's called horizontally, where we take and we split the data up across multiple physical database servers and then come up with some kind of mechanism to make it appear to the outside world that it's still just a single database machine. The other way to scale a database is called vertical scaling, which basically involves installing a bigger, faster, more capable server machine and take advantage of its increased performance. What this distribution independence idea says is no matter how we've got the data actually physically stored, whether it's in kind of one giant central machine or if it's stored in a bunch of different pieces across multiple machines, from the point of view of the application, or from the point of view of the query language, you might think of it that way, it should appear as if it's just stored on a single computer. Again, it's another level of abstraction that their applications can take advantage of to simplify their internal logic and their design and whatnot by just relying on these rules that the database management system is going to impose. Finally, rule number 12, non-subversion. If a relational system has a low-level language, that low-level language cannot be used to subvert or bypass the integrity rules and constraints expressed in the higher-level relational language. And of course, we know that this higher-level relational language is none other than SQL. What we're saying here is that if the database has some other mechanism for accessing the data, whether that's a different API or, say, a library that lets you go in and monkey with the data files directly or something like that, that there shouldn't be any way that's supported by the database system that allows you to do any of those lower-level operations that would in any way subvert or harm or make less effective the integrity rules and the constraints like primary key constraints, foreign key constraints, that kind of stuff. We shouldn't be able to work around those things no matter how we access the data using the system. So it's kind of the no cheating rule, right? And we want to make sure that there's just no way to work around the fundamental commitment that the data management system is making in terms of relational integrity and key integrity and those sorts of things, regardless of how we access the data. And again, this was kind of a more common thing in the earlier going where we had other mechanisms to talk to the data. Any longer, most of the relational database systems really don't support much in the way of doing that unless you kind of roll your own, right? You can still go in and make changes on the disk to the data that are being stored by the database, but at that point it's kind of on you, right? It's not like the database itself is providing a way for it to be easy to integrate your program with some other lower level access mechanism that would allow you to subvert other things going on in the database, thereby compromising integrity and those types of things.